Hello everyone and welcome back to this Nanophotonics and Plasmonics course. Today's video is on chapter 3 and we're going to discuss about nanoscale optical microscopy. As I mentioned already earlier, nanophotonics were interested in very small objects, and due to the very small size of these objects, we actually need to use highly focused optical fields in order to achieve the resolution which is necessary to study them and image those small objects. So there are four types of configurations that can be used in microscopy, depending on how you actually illuminate your system and how you actually detect the optical signal. So the most straightforward is the far field configuration, when you send light through a lens, an optical lens from a source, propagates in phase space, reaches the sample, and then you detect the light also in the far field. But you can actually use also a combination of far field and near field detection and illumination configuration. So either having a far field illumination coming from a source propagating free space, collect the near field from a nearby optical probe, or on the other way around, sending light in a near field configuration through an optical fiber, generating evanescent fields at the surface of this fiber apex that will interact with your object and basically collect the far field. And then of course you can have this near field configuration where you can send light through an optical fiber, generate evanescent fields that will interact with your object, and then you collect the response in the near field through the same optical fiber. So before we actually dive more into some examples of near-field microscopy, there are a few fundamental concepts I need to introduce first. So typically when you have light fields, they propagate along a certain direction. So in this particular example, we have some kind of green optical excitation. It propagates along the z direction. Now in a transverse direction, which could be the x or the y direction, there's only a very slow spread of the optical field. So that's basically allowing us to say that the z component is almost the wave number, and the kx and the ky are extremely very small. This approximation allows us to expand the z component of the k vector into a Taylor series. This expansion is called the Paraxial approximation. It's also known as Gauss approximation or small angle approximation. Because we are looking at a very small angular dispersion of the optical fields. And this is very important because it allows a lot of simplification when you have to deal with Fourier integrals in wave optics. So this is also very important when you deal with complex beams. So for instance, if you have a fundamental laser beam with a linearly polarized Gaussian field distribution, you can actually use a combination of Fourier transform and Paraxial approximation together with this angular spectrum representation we're going to discuss in a minute. And then you can obtain a Paraxial approximation of the Gaussian beam. So this is the electric field in the Paraxial approximation of your Gaussian beam. So we're not going to discuss extensively about each of these terms here, but the few key elements I want to mention is that this W function is the beam radius. So if you have this Gaussian beam propagating along the z direction, you have the beam waist here, and the radius of this beam waist is called the beam waist is W node. But if you look at a given position z, the radius of the beam after a certain dispersion is given by this function W of z. Then you have also the radius of the wavefront. You have this function eta, which is just a phase correction that describes how the phase of the beam will actually change as it propagates along the optical axis. If you take a cross section of this beam in a transverse direction at any given position, you have this Gaussian profile for the electric field. So this is the Paraxial Gaussian beam. which is valid only for weakly focused beams, because we are in the paraxial approximation with only small angles. Something which is also very important is that there's actually a phase shift that occurs when this Gaussian beam propagates. So if you start close to z approaching negative infinity, and you launch both a Gaussian beam and a plane wave, or both in phase, by the time they reach z equal infinity, then they become out of phase by 180 degrees. So the Gaussian beam is actually gradually shifting in phase with respect to a plane wave. So within this approximation, the electric field to calculate from a Gaussian beam in the paraxial approximation is no longer a solution of Maxwell's equations. So the other thing I need to mention is that when the beam waves of the order of the wavelength of light in this particular medium, then you would need typically higher order terms in the Taylor expansion for this paraxial approximation. Another important aspect of Gaussian beams is that they do not exist, no matter how rigorous the theory that describes them. The reason for that is that the Gaussian beam profile demands a Gaussian spectrum. However, the Gaussian spectrum is infinite, and it contains evanescent components that are not available in a realistic situation. So therefore, a Gaussian beam must always be regarded as an approximation. And this is the reason why this electric field here does not satisfy Maxwell's equations anymore. To give you a quick example, there are different type of families of Gaussian beam modes that exist out there. These are just the two most famous examples, the Hermite Gaussian modes and the Laguerre Gaussian mode. So I'm not going to discuss that. It's more just illustrative to show that there are different type of Gaussian beams out there, and this is just subject to a whole special area in the field of laser physics. I mentioned earlier about this angular spectrum representation, and this is just a technique that involves the expansion of complex optical fields into summation of infinite number of plane waves. So if you look at any type of realistic configuration where you have a system, an incoming wave, an incoming field, you have some scattering fields, and if you're interested in what's the electric field at a given location in space, it's going to be just superposition of both fields, so it can become very messy. Even if you know an analytical expression for this incoming field, the fact that you have a scatter field that's superimposed on top of that makes it very hard to actually estimate what's the field in there. A way to do that is using this angular spectrum representation, which is just a summation of those different plane waves. So you have an infinite number of plane waves with different K vectors that you sum over the entire reciprocal space to obtain your field at a given location. So if you're looking at very far away from your system, you're looking at the far field, and this far field actually connects to the near field. This is the relationship that exists between the far field and the near field in any given system. So something also which is very important to notice is that those far fields that you actually calculate here within this framework of angular spectrum representation and within the paraxial approximation are in agreement with Fraunhofer diffraction theory in wave optics. The last part that would be discussed in this video is dedicated to focusing of fields. So it's something very important. This is a driving force of optical microscopy. So why we need to pay attention to focusing of fields, simply because the smaller the laser spots, the higher the resolution. The higher the resolution, the smaller features you can actually image. Light focusing is actually dependent on two different factors. First, the optical field itself, the wavelength, the polarization, and the angle of incidence. and second, the optical setup itself. So the lenses, the polarizers, and the analyzer. So these are just two examples. The first one here shows 3 different laser beams, red, green, and blue ultraviolet, that are passing through the same optical setup. So you see that the red laser is more highly focused as compared to the green one and to the blue ultraviolet laser. And the bottom example here shows same optical excitation passing through different optical setups. You see that you have achieved different focus of this laser spot. So highly focused laser beams are used everywhere in optical spectroscopies, and they present limit in terms of light confinement. So we discussed about this light confinement, which is the diffraction limit, and we mentioned that this has been theorized by Abe and Rayleigh independently, and they predicted a theoretical limit for this for the resolution, which is about half of the wavelength you use. So we can achieve a better resolution in confocal microscopy, and we're going to discuss about confocal microscopy later, of about a quarter of the wavelength. So if you send an incoming field onto this anaplanic lens, you need actually to consider this optical element also if you want to achieve higher resolutions. How you actually describe this lens? You need 2 rules. You need to follow the sign condition, which is just geometrical optics, that's gonna dictate how the light rays, the conjugate light rays, will actually behave and be refracted. You need also to consider this intensity law, which is looking at how much energy is transported by the conjugate ray and how much energy is actually outgoing from the optical setup, and it's just energy conservation. So you can actually end up showing that the fields must satisfy this relationship. So this is the electric field which is going out of the optical setup, which is being refracted. This is the incoming field that you send onto this aplanic lens, this optical setup, and these are the refractive indices on either side of the optical element. These are the magnetic permeabilities of the media on either side. So because practically all the media we are considering here are non-magnetic, so mu1 and mu2 are actually equal to 1, so we can actually neglect this term. Something also we need to consider is the back aperture. So the back aperture of a microscope objective is a few millimeters in size. This is a photograph of high performance confocal microscope objective, and this is just the cross section that shows the breakdown in terms of optical elements. You see it's very complex. There's a lot of lenses and optical elements in there. However, we don't necessarily care about how light goes through here, but rather we need to pay attention to how light comes on the back aperture. So in order to fully use the numerical aperture of this objective, the incident electric field you're sending onto the back aperture needs to fill, or actually overfill if possible, the back aperture. So what's the filling and underfilling? So this is the schematic of the objective and the back aperture, which is a few millimeters. If you're sending a Gaussian beam, which are certain beam waist, onto this back aperture, if the beam waist is fairly large and covers the entire back aperture, this is what we call the filling. Underfilling would be that the beam waist of your Gaussian beam is actually much smaller than the back aperture itself. What's the importance of that? Well, if you're actually filling or overfilling the back aperture, you're going to obtain an even illumination across the field of view where you're actually trying to image the small objects. However, if you're underfilling, you're going to end up with an uneven illumination. and you're gonna have artifacts that will actually deform your image. You're gonna have vignetting and ellipticity that will actually show up. So if you consider a Gaussian beam and focus this on the lens, you can actually calculate the filling factor f node by taking the ratio between the beam waist over the lens aperture radius. So this is the factor here. So it goes all the way to 1 when it's filled. So let's look at the influence of this filling factor on the sharpness of the focus. So if you're looking at in the plane where you're actually trying to image your object, so in the object plane, the electric field distribution, the spatial distribution, so along the x or the y direction, you look at the field intensity or the intensity of light, which is distributed in this plane. When you have an underfilling or a low filling factor of 0.1, which means that the beam waist is 10 times smaller than the back aperture diameter, then you obtain a very large laser spot. So this is the spot that you obtain to actually illuminate your object. As you increase your filling factor by increasing the beam waist, you see that you have a narrowing of your focus. So the light is being more and more focused as you reach very large filling factors. So this is filled and this is overfilled when you have filling factors larger than 1. So light here is polarized along the x direction, and you can see that for low filling factors you have basically only one curve, so you have only the continuous and dashed line that are overlapping, meaning that this spot has the exact same profile along the x and the y direction. However, when you start filling and overfilling the back aperture, you see that now you're starting to have actually a laser spot which is more focused in one direction than the other. So this is the dashed line is the x direction where the light is actually polarized, and the other one is the y direction. So it's actually more focused in the direction orthogonal to the polarization. So this high resolution has a cost, and it's called ellipticity. So this ellipticity is shown by the fact that light is actually polarized. So you have actually a polarization effect, which is due to the vector nature of the field. So you want to fill the back aperture, but this has a cost, and it's actually deforming your image, and you have an ellipticity phenomenon that occurs. Also, these overfilling here correspond to a plane wave. So if you send an actual plane wave, you're overfilling the back aperture, and you have the highest ellipticity. This is the field intensity in the plane containing the propagation direction. So the field is actually propagating along the z direction. So you have the z direction. The field is propagating along the z direction. Light is polarized along the x direction. So this first image on the left shows the local field intensity of a Gaussian beam, which is focused here. So this is the focus of this Gaussian beam in free space. So this is a homogeneous medium or free space, and focused on here. And the other one is basically the same, but now it's along the y direction, so the direction orthogonal to the polarization. So the field is polarized along the x direction. So very similar to what I've just mentioned before. If you're looking at how focused is the beam here at the beam waist along this direction, you see that it's actually larger than here. So the beam is actually more focused in this y direction, which is orthogonal to the direction of polarization, than in the x direction. So this ellipticity is clearly shown here when you're looking at how your Gaussian beam is actually focused in a homogeneous medium. Now, most of the time, we actually are not interested in focusing just a Gaussian beam in free space. We are actually looking at cases where you have a substrate, you have an interface, simply because samples are generally supported onto a substrate and beams are focused on lenses. So the optical fields are always focused near an interface. So it could be on the interface, below the interface, above the interface, but near an interface. So what's the field distribution of a Gaussian beam look like? What does it look like around the interface? So on the left-hand side is the uniform medium I've just mentioned, the Gaussian beam in a homogeneous medium. And then when you have a glass-air interface, if you send a plane wave or Gaussian beam onto this interface, which is, you can see the propagation here, something we've seen also in chapter 2. I've shown some simulations of plane wave propagating. A lot of things can happen. So you can have the formation of evanescent wave at the interface when the angle of incidence here is actually equal to the critical angle. In this particular case, the critical angle is 41 degrees because we have a glass-air interface. And then we have also some standing waves that are actually forming in the denser medium, with just the superposition of the incident field and the reflective field. So we have the total internal reflection because we are at an angle which is larger than the critical angle. So in this supercritical condition, we have the formation of standing waves in the substrate. So it's something that you need to consider because it has some applications that we're going to discuss in a minute. Now, what about the other direction? So this is the Z and X direction. So we are in the plane of incidence. But now if you're looking at the direction orthogonal, similarly to what we had before, where it's more focused in the direction orthogonal to the polarization, we have also clearly here a more focused spot when we're looking at the direction orthogonal to the polarization. So it's something which is not only in uniform media, but also at interfaces. So when you have interfaces, you have to account for this ellipticity effect. We have to also take into account the fact that you have evanescent waves, standing waves forming as a result of this interface. To conclude on this, I wanted to show you a few experimental images that are mapping of the optical intensity at the focal point for a glass-air interface and glass-metal interface when the laser beam spot is actually focused just above the interface, at the interface, or below the interface. So what you can see here in a case of glass-air interface, you have those concentric rings that occur where the laser spot is to be focused. And those rings are the manifestation of those standing waves I've mentioned just before. So as a result, even if you try to achieve a very strong localization, strong focus of the laser spot, you still have those concentric rings that are the result of this total internal reflection at the glass-air interface. On the other hand, when you look at the glass-metal interface, due to the different in contrast between the two different media, you do not observe the formation of these standing waves in either side of the interface, and therefore you can achieve very strongly, nicely focused laser spots.